Hello! Today we are going to have a look at this Tektronix scope. Scopes of this line, TDS 500 and also 400 and 600, are known to fail because of leaky electrolytic capacitors. I have already repaired a few such scopes before I started making videos, and one of them I still have. I used it in many previous videos. It is the same model as this one, 540A. Another scope I repaired was 620A, which is 2 gigasamples per second, but it had only 2 channels, so I preferred to keep my 540A, which has 4 channels. And one more reason was deep memory option, which my 540A has. And this scope also has deep memory option, but it also has FFT option, so if I am lucky with this repair, I will have a chance to upgrade my scope. I bought this scope on eBay for $200. It was sold by some sort of an electronics recycling company, which is not far from my place, so I picked it up myself and didn't pay for shipping. Let's try to turn this thing on. These scopes are quite noisy, and they also take quite a while to boot up. It's probably better not to turn it on, so that not to make the problem worse. But I just want to show you the symptoms. So this constant beep is not normal. There you go, it booted up. So as you can see, the symptom of the problem is here, multiple self-test failures. Sometimes such scopes don't even boot up, and I tried repairing one of those, but I didn't succeed. The corrosion on the board was so bad that some traces were eaten away, and I found a few, but it still didn't boot up. So after quite a bit of struggle, I gave up and sold it for parts. I'm hoping this one is not going to be so bad. Let's have a look inside. Here is the back of the unit, and options 1F and 1M are marked here. 1F is floppy drive, 1M is deep memory, and here we have a sticker, version 2, option 2F, which is FFT. Here we are. So we have 3 boards to deal with here. This main processor board on the top of the unit, the acquisition board on the bottom of the unit, and smaller board, which is the front panel. In this version we also have tiny board here for the printer port and the serial port. It also has, I see, a few electrolytic caps. So here I see some corrosion around this switch next to this capacitor, and I see liquid stuff from this capacitor on the board and here as well. And check this out. This capacitor is just soaked in this corrosive stuff, which must have leaked from this cap. Here is the bottom, and here we see the acquisition board, and this smaller front end board There are no capacitors, electrolytic capacitors on this front-end board, but a lot of them on the acquisition board. And I see a really bad corrosion here. Can you see corrosion on the pins of this chip here? And check this out. This looks pretty bad. Here I removed the main board, the acquisition board, and this small interface board. And the way to remove the front panel is this. We need to gently pry this top open to release the plastic latches, and then gently pull it off. So now the top part is off, and now we do the same thing on the bottom. Gently pry off the latches. There you go. Alright, so we took off the frame. So now it's really easy. There you go. And now we need to be careful with this. There you go. Here is the front panel board. Here is the date on the acquisition board. Seems like 8/2/93. And on the main board here, 9/22/93. Here is some corrosion on the pins of these two big chips. This is really ugly. So, we have 96 capacitors to replace. Yes, we need to replace all of them. And they are of two types, 33 microfarads 10 volts and 10 microfarads 35 volts. Here I have a couple of reels which I picked up on sale in a local electronics store for just 10 bucks per reel. And this reel is 10 microfarad 35 volt capacitors, and that reel is 33 microfarad 10 volt capacitors. So I will start with the acquisition board because most of the capacitors are here. I will remove the 33 microfarad ones first, then thoroughly wash the board, then solder the new capacitors, and then remove the other kind, 10 microfarad ones, then wash under them again, and then finally solder 10 microfarad capacitors. To remove the capacitors easily, I use two soldering irons. One is this wonderful soldering station, which I always use, and another one is this unregulated iron, which I almost never use. So I do it with both hands. heating up capacitors from both sides at the same time, and with some practice it's not too bad. I'll show you. For best results, I tried to scrape off corrosion from those soldering joints and put some flux. There you go. Here we are. I removed all 33 microfarad capacitors. It seems like I miscounted before. I had 47 and 19 here. So 46 are sitting here and 2 are still soldered to this little board. Not convenient to desolder with this method. Perhaps I need to desolder this little board first, which is really easy to do. I have a desoldering station with vacuum for desoldering through hole components. I don't remember how did I do this with my 540A scope, which I repaired several years ago. And I do remember about 620A scope, and I still have a photo of the acquisition board. And the acquisition board there is completely different, and there is no such board on it at all. And besides these two capacitors, I need to clean the pads with this wick and wash the board. Alright, I cleaned the pads and desoldered this little board. As you can probably see, there is some corrosion on it as well. Now it's time to give this board a really good cleaning. The most drastic approach would be to start with a mild cleaner like this, for example, and then use distilled water to wash and rinse the board, and probably use alcohol after that. But I don't feel like doing this drastic thing right now. I will just use alcohol and toothbrush to scrub it everywhere really well, and we can always come back to the cleaner and distilled water approach later if using alcohol doesn't fix the problem. The first round of cleaning is done. I'm using compressed air to force the alcohol from under the chips so it can carry away all the dissolved junk, and I've done it several times. I'm using 91% alcohol. I could use pure alcohol with no water at all, but I think it's better to have some water to dissolve whatever is not soluble in alcohol. Alright, I soldered the 33 microfarad capacitors, 46 of them. And now I'm going to remove 10 microfarad capacitors. Alright, 10 microfarad capacitors are removed and the pads are cleaned. They're ready to solder new ones. The acquisition board is done and this little board is back in place. All the boards are done except this small interface board, and I put the boards back into the scope. Let's give it a try. No luck so far. One of the error messages is still there. So it's time for more drastic measures. Let's check the operation really quick. Channel 1 connected to the probe compensation. It shows the signal, but it doesn't trigger at all. Let's go to normal mode, and here we are. It doesn't trigger at all. Let's see if I can force. Yes, I can force the trigger. Channel 2. Let's change the trigger source to channel 2, and it doesn't trigger. I can force it, but it doesn't trigger at all. Same thing with channel 3 and channel 4. Here is the error log. I booted the scope several times, so there are multiple messages here. The latest message is about some parameter which was expected to be very low in this range, from 2.5 times 10 to the minus 9th to 1.2 times 10 to the minus 8th, but the actual value was 0. And above there is a message about DAC range test failure. There is a DAC on the acquisition board to set certain voltage offsets and perhaps the trigger level as well. So I turned the scope upside down. Here is this DAC, and I started checking voltages all around the place, and I think I found a problem. Let's have a closer look. So here, not far from the DAC, there is a quad op-amp, which is classic TL074, and I checked power rails on it, and I think the negative rail is wrong. So let's check. The negative lead goes to the ground, and on this capacitor I see the positive 5-volt rail, which is a tiny bit low, but not a problem. And on this capacitor I see the negative 5-volt rail, and on the op-amp pin 4 is the positive rail, and it's there, and pin 11 is the negative rail, and it's not there. And here is a ceramic capacitor right next to the op-amp, and on the side closest to the op-amp I see this negative rail, and it seems to me that a trace going from the side of the cap under the chip, and it's probably corroded there, not reaching pin 11. That's what I suspect. So I opened my scope, which is identical, and checked, and sure enough, in my scope this side of the cap is connected to pin 11, and in this scope it's not connected. You see, we should hear the sound, but there is no connection. With some very careful soldering, the connection is restored. We still have a problem, but it started triggering. I checked all 4 channels and the triggering is working now. So I continued checking voltages across capacitors and power rails on the op-amps, and I think I found 2 more problems. One of the problems is here on this op-amp. Pin 8 is the positive rail and there is no power here. It is connected to this capacitor, and I would have hard time figuring this one out if I didn't have a working scope. So I checked the working scope and it turns out this should be connected to this spot. There is a trace between this capacitor and this resistor and a via, and in the working scope this spot is connected to pin 8 and there is no connection here. And the second problem is around here. Pin 8 of this op-amp is connected to the positive 5-volt rail, and I checked the power is present here, and there is a trace to the positive pin of the capacitor, but there is no connection and there is no voltage across the capacitor. So it seems to me that the only consequence of this is that the bypass capacitor is not connected, so it can lead to some noise on the 5-volt rail around here. More careful soldering this little wire here. And this one here. Check this out. It passed the self-test. And it passed the signal path compensation test as well. It seems like I got myself a working scope. And by the way, just out of curiosity, let's check how bad these capacitors are. We are at 1 kHz, and let's set the second parameter to ESR. And let's start with the new 33 microfarad capacitor, just for reference. There you go, about 30 microfarads and 1.2 ohms ESR. And the capacitance is a little lower because of 1 kHz. It's gonna be closer at lower frequency. Let's try at 100 Hz. There you go, 33.7. But for ESR measurement, it's better to have higher frequency. So let's go back to 1 kHz and let's bring back the ESR. And now for reference, 10 microfarad capacitor, also a new one. There you go, 8.2 microfarads, 5.7 ohms ESR. So now let's check a few random 33 microfarad capacitors, which I removed from the acquisition board. And there you go, 1.6 nanofarads, and the ESR is out of scale, completely dead. Let's try another one. Same thing. A few nanofarads and no ESR. Completely dead. Let's try one more. Same thing. And one more. Same thing. And one more. The same thing. And let's try a few 10 microfarad capacitors. Exactly the same thing. Completely dead. Completely dead. Same thing. I've seen much better. One of the scopes I recapped had half of the capacitors almost fine, maybe with slightly higher ESR. But these guys, which we randomly checked so far, are completely dead. This little interface board is recapped as well. These 4 chips on the acquisition board are running quite hot. Check this out. The first one is running at about 95 or so degrees C, and the next one I see 97.9, and the next one I see 100 degrees C, and the next one is a bit cooler for some reason, about 90 degrees C. And I suppose this is normal because it's exactly the same in the other scope, which I had for several years. And I hope it's gonna be a bit better in the closed case, because now I disrupted the airflow. I found another problem. Here we have 15 MHz sine wave, and the sampling rate now is 1 gigasamples per second, and the time base is 50 nanoseconds per division. It's a bit jittery here on the screen, which is not normal, but look at this. If we change the time base to 20 nanoseconds per division, and the sampling rate goes higher than the real time, so now it is equivalent time sampling, look what happens to the wave. And let's go even higher. So now it is apparent that there are some gaps in sampling. It seems to me that there is some problem with data pipes, perhaps another broken trace somewhere, and this is happening on all 4 channels. A few weeks later. I didn't have much time lately, so I worked on this scope little by little during many evenings. Sorry I didn't document each step. First of all, I tried putting this CPU board into the working scope, and I saw those gaps in the waveforms, so it must be responsible for those gaps. And second, I tried putting this acquisition board into the working scope with good CPU board, and I also saw some problems. First of all, that jitter when this waveform was not quite stable, we've seen that before, and I saw some gaps in waveforms as well sometimes, and sometimes self-test failed as well. So I started looking into the acquisition board, checking the traces and vias around the capacitors, and I couldn't find anything for quite a while. And then a miracle happened. I found full schematic for this scope. Before I used this manual for TDS 520B. It has some circuit description and some schematics, which was much better than nothing. It gave some idea of what's going on, but the schematics are very different from 540. And then I found this topic regarding TDS 644A on the EEV blog forum, And here somebody posted this link to this site. And among other things, look at this full schematic for TDS 540, 544 and 620, 640, 644. Wonderful. So, having the schematics, I started checking the connections and voltages everywhere, and I found a problem here. Pin 3 of this op-amp must be connected to the ground, but it was not. So I fixed it by soldering this little wire, but it didn't fix the problem. So I checked more and found one more problem here. There is a via under this op-amp and it was broken. So I restored the connection by running a little wire from this pin 7 over the edge of the board to the via on the bottom. Here it is. After fixing these two problems, I never saw self-test failures and waveforms were stable. So I started checking the CPU board. I spent quite some time checking the CPU board, testing the traces and vias around the capacitors, randomly checking different data buses. I used the working oscilloscope to look at the waveforms on the memory chips and such. I couldn't find anything wrong. And then it occurred to me to run the signal path compensation, and the gaps in waveforms disappeared. So it seems to me that those gaps in waveforms were the result of running the signal path compensation before, when the triggering was not working properly. So the lesson from this is, if you fix something on the acquisition board, run the signal path compensation before doing anything else. So now everything looks nice and stable, no jitter, no gaps, and I'm so glad I managed to repair this scope. Having full schematics certainly helped a lot. One more thing I would like to do. These two Dallas chips have batteries built into them, and they are certainly pushing limits of their runtime by now. And as I understand, this chip has a real-time clock and no critical parameters, but this chip certainly has some critical configuration parameters, options and calibration and such. So if a battery fails in that chip, the scope probably won't even boot up. But I don't really want to replace these chips. These are expensive and who knows, probably will work for many more years. So what I've done with my other scope, I desoldered this chip, made a backup, and soldered a socket in its place and put the chip into the socket. So I would like to do the same thing here. There you go, quick and easy, having a good desoldering station. The socket is in place. I'm using this programmer, which is Mini Pro or TL866CS. and I need to use this old laptop with Windows on it to run the software. The chip is DS1650Y, and the programmer does not support 1650, but as I understand, the scope uses this chip as 1250, and the difference, as I understand it, is that 1650 has several partitions or pages which are not used in this scope, so we can read it and make backup as 1250. I read the chip and then run verification just to make sure that reading twice results in the same thing. The chip is back in the socket, and I'm thinking about putting the backup file on some sort of an old, small and useless for other purposes memory card, so I can attach it here with a tape or something. So even if I decided to sell the scope and the battery failed, it would be a relatively simple fix. The card is attached with a label printed on a label printer. Very handy tool, highly recommend it. The scope is back together, and check out the FFT. Here is a service manual for this model, and there are no schematics in this one, but there are performance tests. Here they are, and a lot of equipment is needed here, most of which I don't have. So I had to limit my tests to whatever is possible with the 15 MHz generator plus DC offsets and such. So it's hard to be sure that every obscure feature works fine, but whatever I checked so far looked okay. I hope you enjoyed this repair video. If you did, give it a thumbs up and consider subscribing to the channel. I have a pile of projects waiting. Thanks for watching. Bye!